I'm back after a short holiday break, so therefore welcome to the next tutorial lesson. This is the lesson for the section 7 about data organization. We'll have a look into special solutions for searching in data, and therefore I prepared a small Excel sheet where you can read dates and according weekdays. And you should use this Excel in MATLAB to search for a special weekday or weekday name so that you have a date and you convert it with different search mechanisms to the corresponding weekday. So let's have a look into the different tasks. Task number 1 is the following. Download the file calendar.xlsx containing dates and corresponding weekdays together with the Posix Unix timestamp. Read the file, for example, using the read table function from MATLAB. There's a sample here, read table calendar xlsx, and prepare the data for further use. For example, you can convert the German style format, which is used in the Excel file, to the English format. And then you can think about why such a change might be better for further solutions or comparisons or also runtimes. So let's have a look into the Excel and then into the program how we can read the data. The Excel looks like this. So you have a very simple table. The first column is the date, and you see the German style format where the day with the dot and the month and a dot and the year is represented. So it starts from the 1st of January 2019 and it ends at the 15th of September 2031, and you have the corresponding days here. So it's just that you have a simple database or data set which you can use. In the third column you have one specific thing. Maybe you remember the date which is represented with seconds from the 1st of January 1970. So we already used this, and this is the so-called Posix time or Unix time, and it can also be used as a direct access because you have a number which you can directly assign to a special position. So this is the representation which you have to read in. And if you read the data, you can use the following function. You can read the calendar raw data with the read tail function, and that we all have the same set and that we all have just text as the different types or the different elements in all of the variables. You should use this extension. There is one additional thing which you have to take care on. This additional thing is that, for example, newer versions of MATLAB from 2020, maybe A or B on, you have to use an additional parameter which is called format auto. And this format auto is very, very important for new versions because it just works with Excel tables if you use this. In the older versions, it's forbidden because format auto is just used for special text files. So if you use it here, I have the version 2019, then it will break, it will not work. But I use it without, and you, if you have an earlier version, you use it with format auto. So if you run this, then it lasts a little while, and then you should get the table in the following way in your MATLAB workspace. So you have the different columns. Everything is based on a character string, and you have everything in a mixed version. So therefore, every entry here, every element is a cell with an individual text. So this gives us possibilities to have the same setup, and now we should write the program to read the data. So here we use just the single command. If we write the program, it looks like this. So we always start with CLC clear all and close all in our scripts, so that we have a very elementary setup. I prepared a new file, calendar search step by step, and I will use this for our step-by-step development. And then we copy our function here, our function call, into this program. So the function call contains the file which we want to read, and it contains our pairs of read variable names and read row names, so that the headlines which exist in the Excel file are not used for the naming of a table. So it reads the whole stuff into a table, and as I said, maybe you have to use format auto here, and if you read this, you see this table structure, okay, like shown before. So a table has a specific thing. You see that it is a table. You can also name the different columns here. It's automatically defined with variable 1, var 2, var 3, and it would be possible to select the whole column with calendar raw.var1. But we won't use this. We just use it with a normal indexing. So for us, it's not important here. That we see the different timing behavior or different runtime behavior, I would say that we also add a tick and a tack, which measures the time from the tick on to the corresponding tack or tock, and this tick tock will give us the runtime which is required for the reading. And of course, that we know what happens, we want to add additional comments and also an output for the user. So in this case, this is our reading mechanism. So read the Excel sheet. It might be necessary to have this, and then we do display read data, and with this we can run it now. So let's close the output, and then let's run the program. And you see the reading of our file costs 1.65 seconds. So we can measure our time behavior with this. So let's have an additional look into the data, because in our question there is one thing mentioned which might help us. You see this German format, and it might be better to have an American style format where the year is the first part, then the month happens or comes, and then the day comes. So that you have year, 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 year with 4 elements, month, month with 2 elements, and day, day with 2 elements. Why would this be better? In our set, there is no big improvement if you arrange your program in a specific way. But if you have additional things, like for example file names, it's much better to convert this here to the other direction, because then you automatically get a lexical sorting. Because if you start with the year here, then you can just compare the different characters. So for example, if you have two different dates, you just compare the first two letters and you compare them as long as they are the same, so as they are equal. And if you find a difference, then you can compare if it is lower or greater than. This means that you can compare single characters and you directly get the order, because in the ASCII table or in the ANSI table, all of the characters are ordered. So the character for 0, for example, is lower than the character position for the 9, and therefore you can use this here. In our program, you can, it's up to you. I would suggest this because if you do the following search mechanisms from the largest position to the lowest, you can also use this German format. If you turn it or if you flip it, then you can start from the first position. For file names is essential. If you arrange your file names with these time tags so that you have year, month, day, then you follow with the file name, with the name of the file, then you have an automatic ordering mechanism, and the explorers or other tools will automatically give you a sequential order just by the lexical comparison. So therefore it's quite helpful, and I want to show you how you can do this here with MATLAB. So let's do this. We start again with a short comment and with a short output. So that we know what we do. And then we do our tick-tock again, so that we will measure the rearrangement. And we will see that this rearrangement costs a lot of time, especially because we have a lot of text strings which we have to rearrange, and it costs a lot of time. So therefore it's not really helpful if you do just one search, but if you do several searches, so if you just read in the data like in a database and then you work with the data without any additional rearrangement, then it's helpful. So therefore you should remember that all of the special preparations should be done at the beginning of the data reading, and then you should work with the data. And if you do a lot of search mechanisms, a lot of accesses, then it's really helpful. So what do? We start with a loop. We can use a full because we exactly know the size of the calendar raw data. So we run through all of the elements and we get this size with this function. So size calendar raw, comma 1, which is the first dimension. It's the number of lines or the number of rows. And then we take the data. So we have to know that this is now a table of cells. So if we, for example, get the first element, I show it here, calendar raw. And if we access it, we use the curly braces. And if we use, for example, 2, 1, because in the first line we have the headlines, in the second line we start with the data, then we get the cell array. And the cell array contains our text. So therefore I take this data cell and then I convert this. You can do it with different methods. I do it in this way here. And it should also show you that it is very dependent on how effective you program your code. So, and then I convert this cell. So here I have it in ans. So therefore I can use ans, for example, 1, so that I get the text. And this is exactly what I do here. And then I do the conversion. And the conversion is quite simple. If we look into our data again here, then we do just a rearrangement. So I take these 4 elements, then I take these 2 elements, and then I take these 2 elements, and I rearrange it with a concatenation or with a new setting of a vector to a new arranged setup which starts with the year. So therefore, what I do with this is the following. I take the elements from 7 to 10 in our text. So from here we change to cell, from here we change to text, and I take the first line, and here the elements from 7 to 10, which is exactly the year. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I take this and I combine it to a new element starting with a vector set separated by minuses, and then I take the month in the same style. So I take the 4 to 5. So here 1, 2, 3, 4, 5. It's the month. I take again the minus as a separator, and then I take the day. So with this, I do automatically the rearrangement, and then I convert it to a cell, and I assign it to the existing calendar cell or calendar position, which can be done like this. So the data index is here at the first position because our dates are at the first position. And if I run this program, then I will have the American style representation. So let's do this. Let's run the program. And then you will see that it prepares the date. The problem here is that it costs a lot of time. You will see about 6-7 seconds to prepare all the data. Okay, it lasts much longer because I do a video streaming at the moment. But you see the preparation due to these special formats or special cell structures and complex memory operations cost a lot of time. So you can optimize this, of course, but as I do it just once at the beginning, I don't care on this. But you see, it changed the date from the German style to this minus separated version. So, and now we can go to the next question. Question number 2. Again, just as a repeating, this helps us for the lexical comparison because we can now start, if we have a date, if we have a search date, we can start with the comparison here. So we start comparison as long as we will have equal characters, and if we have a change, then we compare if the search date position is lower or greater than this position, and then we know that the date is larger or smaller than this date here. Okay, so let's jump back to question number 2. Question number 2 exactly deals with these searching mechanisms, with these simple searching mechanisms. So we should program now a sequential search. Do you remember? Sequential search means we start at the first date with a special search date. In this case, we want to have the search date of Christmas 2029, and we want to know which weekday this Christmas day is. So a sequential search always starts at the first entry and goes through all elements until it finds it, and if it does not find it, it has to go through all elements in the principal version. So therefore you use the data from task 1 and program a sequential search, e.g. to search the weekday for search date 2029, December 24th. We should measure the required runtime for the whole search using the TikTok again, and then we print the weekday. So let's do this directly with MATLAB. We continue with our previous program. So we read in our data, and then we do a special version of the entry of the search date, because I don't want to set it in the program. I want to give the user the chance to enter his or her own search date. So therefore we use the input function. Of course, we start with a comment and with a display of what we do now. So enter date for which you want to know the weekday. And then we create the search date from our input. So we use the input function, we prepare the prompt, and then the user of our program is asked to enter a date. And then we do our sequential search. So again, what we do is we print out the next step so that the user knows what the next step is, and we add a comment and we measure the time with TikTok. So the sequential search is exactly the same what we did here. So we run through all of the elements, and then we check the different dates against the search date. So therefore we just use a for loop which runs again from the second column, from the second line to the last line. The first line contains the headlines. And the difference now is here that we have to do a comparison. Comparison is a condition, therefore we use a if. Again, we have to take the data here. So we do exactly the same what we did here, but I want to show you a more effective mechanism. For example, we compare now the search date, and MATLAB is so kind to us that it is able to automatically check if two strings are equal. So you can use the strings in the same way like normal variables or normal matrices. And now I have to take the cell from my matrix and I have to convert it to the string. So in the previous version, I did it in 2 steps with an index access. Here I do it with a special MATLAB function called cell to mat, which converts a cell matrix to a standard MATLAB matrix. In this case, it works because it's one vector with text, and I convert it to a comparable text version. So if I find this, I interrupt my for loop and I stop my complete run here. So if I found this, I have to do a special separation of the tasks, because, for example, if I find a date which is part of my raw data, it can happen that I have the index or that I have the last index of my raw data. The same happens, the last index of the raw data, if I cannot find the search date, because I run through all of the elements and it will end up with the last element. Therefore, I have to check the differences. So the first check which I have to do is if I'm lower than my last index. If I'm lower than the last index, then I can directly print the date. If I'm larger than this, then I have to do a separate check, because I have to check if it is the date which I search. So if the last index contains the date which I search, and then I can just display the weekday. Otherwise, I have to print a warning or an error, or it's up to you how you want to react on a not found search date. So, and this is our program now. If you want to have the measured time very exactly, then you should enter the talk here, so that you also have the comparison as part of our measurement. So if you always print the talk in front of the display, then you will also get the comparison as part of the search. I don't want to measure the time for the printing, because printing always costs a lot of time. So therefore I just want to see the real search, so that I can compare these things, and not that I compare also the display. So let's run the program. It prepares the data, and then I can enter a search date. Our search date is the 20/29/12/24. And if I run the sequential search, I will get that the Christmas Eve is on a Monday in the year 2029. Our sequential search costed 1.4 seconds. So now we can play with this. We can play with different inputs. So for these benchmarks, if you want to test our program, it's always ideal if we find special limitations. So inputs which are limitations, and also inputs which will run into error situations. So therefore, our limitations are the first and the last date which exists in our raw data, and also dates which are outside, so external of our raw data, which are not part of our raw data. So therefore we do this and test our software now with these special limitations. So let's have a look which dates are outside of our raw data and which are the limitations. So we have the calendar raw, and if we select the second date, we will get the start date. So it's the 1st of January 2019, so we have to remember this. And the last one is size of, so we can just copy this here, size of calendar raw. Which is the 15th of September 2031. So these two dates we have to remember. And that I don't have to run all the time the reading and the preparation, I will comment out these lines here. If you want to do it more sophisticated, you can use function, of course, or functions, different functions, so that you have a real work suite now. But I do it just for these tests here in this way. So if I run this, and if I run it with the first date here with our limitations, then you will see what happens. So let's enter the first date. Sorry, was wrong. So then you will find that the first date is found quite fast. And if we search the last date here, so let's run it again. And if I enter the last date, then it will cost more time. So this is exactly the problem which we have in the sequential search. Dates which are in the early stages of our raw data, so which are in the early indexes, can be found quite fast. Dates which are in indexes at the end are found very slowly. So therefore we will have a mean access time, which is the mean between these two times. Let's test also the dates which are outside of our raw data. So in my case, the first date which is outside is, for example, the 31st of December. So let's do this 1 year before. So 2018, December 31. So if you run this, we'll get our warning, our error output, but it will cost almost the same time like the search of the last, because exactly what we have in our program is that it will end at the last index. So all dates which are outside of our search, for example, also here, the 20, 31, 09, 16, which is the next day after our maximum date, will also cost the same time. So you see, we always have something of 1.2 or 1.3 seconds. So for the current situation, it might not be a problem because we have just a very limited set. But if you have millions of data, the sequential search is not really efficient. So therefore, we have to do some improvements. The first improvement can be done if we directly work with these elements which are outside of our raw data. So dates which cannot be found in our raw data. Therefore, if we extend our program with an additional check at the beginning before we start our search, we can avoid runs which are nonsense because the data will not be part of our raw data. So therefore, let's do task B of question 2. Task B of question 2 exactly deals with this. Extend the search with an error output if date is before or later than the time interval of the data in the raw data. So let's do this. First of all, I do exactly a copy of my search mechanism, because I want to do it each time I run the program. And then we extend our program with an additional check at the beginning. So for the additional check, I have to remember if the date is outside of my raw data. So therefore, I will take the start date and the end date. And this time I will put it as part of my time measurement because it directly is a part of this check. So I take the start date and I take the end date from my matrix with this cell to match. The same what I do here, that I have it available. And then I can use a special mechanism which will find an index where the start date and the search date is different to the start date. So what I have to do is the following. I have to compare the search date with the start date first. And I want to find indexes where they are different. So I can use the function find for that, because it will return all indexes where this is true. And then I go to lexical check, where I assign it to lexical check. So this is my comparison. And then I check if the lexical check is larger than 0, and if the search date of the first found index where it is not equal is lower than the start date, because then, according to the lexical search, it is it is lower than the first date, or the text is lower than the first date. In this case, I print a warning. So what do I do here again? I check if I already find a difference. So if the dates are the same, then I will have an empty vector. So length will be 0. So if length is not 0, then I compare this. If they are equal, then my search will work. And then I compare the first difference. The first difference is the first index, which I find here. So if I compare the first index of a difference in the search date with the first index of a difference in the start date, and if the search date part is lower than the start date part, I know that the search date is lower than my start date. And if it is like this, I stop my time measurement and then I print my warning. If not, I do an additional lexical check if my search date is larger than the last date. So this was smaller than the first date. Now I do the check if it is larger than the last date. Here I do exactly the same. So I do a lexical check with a search date, but now with the end date of the raw data. And then I compare it in the same way. Just now I do a greater than with the last date, with the end date. So here I did a smaller than or lower than, and here I do a greater than. Otherwise, I can do my normal for loop. So this is exactly the same what I did as a for loop. And now I can avoid this additional check because I checked it in advance. And therefore, if I find something here, I can just print it. So therefore, I don't have to use an additional conditional check here. So if I find something, then it's a correct output. So that's it. With this, I can do my check, and it will react quite fast for dates which are not part of my raw data. So let's test this. If I enter dates outside of my raw data set, this is the first run where we don't have the check, and this is now our new run where we have the check. And you see, for dates which are outside of our raw data, it's quite fast. Again, for the date which is larger than our data set. So the first run without the previous check will need the 1.2 seconds as before, but the new check will speed this dates which are not part of our raw data set up in a quite tremendous way. And all other dates will cost the same. So for example, if I do this, it will not be so much difference. You see, it's almost the same range. So we already did an improvement. And now let's get to question C of question 2. Question C is exactly the combination of what we already did. So you should play with different search dates and what would you expect concerning the measured runtime. So again, I want to repeat, if you have such question, it's always the best way if you do your benchmark with a special limit situation. So the limits are always dates which are not part of ours, so which are things which cannot be found anyway, or with dates which are at the beginning or at the end. So if you need the longest time or the shortest time. And therefore, in basic case, you don't have to test all of the things here. You just test the first date and the last date, and you test dates which are lower or greater than your raw data set. And then you will find out that exactly what you know from the lesson will happen. Dates which are outside of the raw data will be found or will be returned easily if you do an additional pre-check. Otherwise, the sequential search will last longer for dates which are at the end of the index set. So at indexes which are at the end, the search will run a long time longer, and indexes which can be found at the beginning or dates which can be found at lower indexes will be found very fast. So therefore, it's ideal, it's not so ideal for the normal data sets. If you have just very small sets of data, it doesn't matter if it costs 1 second or 0.5 seconds. But if you have millions of data, then you will have large impacts on your runtime performance. And therefore, we have to improve our search mechanism. But before we do this, there is one additional question available. If you remember the tasks which we did, so the search which we did, then you will see that different runs, so if we run the program even with the same search date several times, we'll always get different runtime measurements. So from 1.2 to 1.3 to 1.4, there's a range which we get as an output just for the same date. And therefore, we have to think about why does this happen. So what is the background of this? And therefore, you can jump back to our lesson which we had about operating systems. Do you remember what happens if you have a preemptive scheduling? So if there are several programs available at the same time and share one resource, here you have to use it. So TikTok does not really measure the time which is exactly required for your part. It measures also the changes, these parallel changes to other programs. For example, at the moment, I do a recording of the video stream. I have open PDF, I have open Word, and so on, or Excel. And therefore, there are several programs which are all the time shared and which are all the time preemptively scheduled on my processor. And therefore, I will have different runtimes. So TikTok just gives us a small hint about our pure runtime, but it will also have additional measurements, for example, for the changes between the different processes, or also between different internal runtimes in MATLAB. So therefore, it's not an exact or exactly measured runtime. It's just something around. So you should measure several times, and then you should create a mean calculation, and then you will get something about what is really required for the different scenarios. Okay, therefore, the question D of part 2 exactly deals with this. So why is this TikTok so different between different runs? It's exactly, go back, if you don't remember, go back to the operating system, and then you will know from what I'm talking about. Okay, let's go to question 3, which is the improvement of the search, and it's directly the jump into the fastest version. The fastest version is the index search, because if you're able to calculate from a search date or from a search pattern directly the index where the corresponding information is located, then you will have a faster search. There are some slight, let's say, improvements also if you deal with characters, but let's go step by step through these tasks. In task 3, we want now try an index-based search using the number of days as an index to the calendar data. Before we start with this, we have to think about how we can calculate our correct index. So what do we need for the calculation of the days? Usually each year has 365 days, but there are some special years, the leap years, and therefore if we have these leap years, we have to add one additional day. So therefore what we have to do first, we have to calculate if we have a leap year or not. So we create now a function which does this. I already prepared this, so the function returns a result and is called leap year and has as an argument the year to check. So for example, if I enter the year 2000, it will check the year 2000 and it will return a 0 or a 1. The leap year can be calculated in the following way. So if the year is divisible by 4 and not by 100, then it is a leap year. So it must be an integer division so that there will be no rest. Therefore, I can use the modulo function, which tells me if I have a rest available. So if there is no rest, it is divisible in an integer version. So in this case, if I divide by 4, so if I divide the year to check by 4, and if I have no rest, it means I can divide it completely. So if I divide it completely, then I have to do the additional checks. If I cannot divide it by 4, then it's not a leap year. This I can do because 100 and 400 is also divisible by 4. So if I divide by 100 and if I have no rest, then I can divide it. This means that it is not a leap year if it is not divisible by 400. So if I divide it by 100, I have to do an additional check. If it is divisible by 400, then it is a leap year. If it is not divisible, then it is no leap year. If I cannot divide it by 100, then it's automatically a leap year. It means if I can divide it by 4 with no integer rest and it is not divisible by 100, then it is a leap year. If it is divisible by 100 and if it is divisible by 400, it's a leap year. Otherwise, it's not a leap year. Oh my God. So therefore, we can use this leap year function to calculate leap years. So for example, if I use it in the following way, leap year 2000, then I check if 2000 is a leap year. 2001 is no one, 2002 is no one, 3, 4, and so on. So you see, we always get a 1 if we have a leap year, and we always get a 0 if we have no leap year. So with this, we can automatically check our years if we have to add 366 or 365. Why do we need this? We want to calculate the index. So therefore, if I open the raw data again, therefore we start with this date and then we add the number of days which we have as a distance between the search date and the start date. And with this, we directly have our index. So the number of days between these two dates. So this is index 0 in principle. So we have to add additional position because we start at the index 2. But then we can calculate, and each time if the individual year here is a leap year, we have to add one additional day in addition to the whole days for 1 year. So let's do this. Again, we start with a small output. So we add our existing program so that we can compare the outputs. And then we start with a small output and with our time measurement. So, as we're so efficient, if we do previous checks, then we can directly do these previous checks here. And in this else part, we will do our measurements. So we don't need this talk here because we always do the talk, the end of the time measurement, before we do our output. So therefore, we will do it inside here. Okay, so and now we have to do our index calculation. For our index calculation, we need the start time, so the first date, and we need the search time, and we need it as days. So therefore, we can do the following. First of all, we extract the year, the month, and the day of our first date in our raw data. We do this in the following way. We go to our start date of raw data, which we already created here. We select the first 4 elements, which corresponds to the year, convert it from string to number so that we have the year as a number representation. The same we do for the month, and the same we do for the day. So the year is from 1 to 4, the day is from 6 to 7, and the month, the month is from 6 to 7, and the day is from 9 to 10. The same we can do for our search date. And also for the day. But as we already use our search day as the rest of the month of the days which we need for the index calculation, so that the rest of the month of our search year is the number of days, therefore we can use this directly as an index. Therefore we can directly start with this day count or day index with the search day. The only thing what we have to take care of is that we start here, if I go into the raw data, again at the second position. So therefore we have to add 1 additional day to go into the correct index. So therefore we add 1 for the headline to come to the correct index. So, and now we have to add the month to our day count. Day count is the index into our raw data set. So what is easily, or what can easily be done is if we prepare a vector where we have all the days for each month available. So January has 31 days, February has 28, March 31, and so on. The only difference is now here, the February, for the leap years, we have to add one additional day for February. So for all dates which are after February, we have to add 1 additional day if we are in a leap year. So first of all, what we do is we just add to day count the sum of the days for the individual month. So we can do this with sum. and we run from 1 to search month -1. Because the last month has already started and is represented by the days, and the days is already counted, therefore we subtract 1 for the search month. So if we are in May, we will add January, February, March, April. So these 4 elements and not the 31 in addition. So the days for the last month, or the month which is represented in the search month, is calculated with the days of the search month. So therefore we subtract 1. While we sum up all of this and we add it to day count. And then there's this special check. If we are in a leap year and if the search month is larger than 2, so if we are here, then we add 1 additional day. So we do an additional check. And this additional check uses our new function leap year, which takes the search year. And if the search year is a leap year, and if the search month is greater than 2, then we add 1 additional day. And now we have to sum up the years. So for the years, it's not so easy like this. It would be possible if we create a corresponding vector for the years which are represented in the let's say raw data, but for each leap year we have to add 1 additional day. We create a loop which runs through all the years and adds 365 for the normal years and 366 for the leap years. So let's start with the first year, which is our start year from the raw data. And then we run as long as we reach the search year. For the search year itself, we don't have to add this 365 or 366 because it's a started year, and therefore the rest is always represented by the month and the day of this year. Within this while loop, we add our elements. So if it is a leap year, we calculate 366 to the day count, and if it is no leap year, then we add 365. And to get a correct run, to go through all of the years in the while loop, we have to add the counter of years. So we run starting from the start year of raw data, always add 1, so that we run through all of the years until we reach the search year. We don't have to take care again if search year is smaller or greater than the year count, because we did our check in previous ahead to this complete check or calculation. And therefore, we can now just print again the output where we use the calculated day count as an index to our data. So what we do is we use the day count now instead of other elements which we used here, and directly use the calculated counter. So let's run the program. If we add again our specific day, the 2029 12/24, then you will see the different run times. And if you compare this, you always get the correct output, but you see that our index-based search is quite fast. So it is even fast if you use one of our limit dates. So for example, if we go to the year 2031, 9th, 15th, which is the last date. Even here, we are quite fast and there's no big difference. So it's a very similar time delay which we require for the search. Let's do again. Okay, you see, it's quite fast. And this happens because we are just doing calculations and then we directly jump to the right position. So we don't have to do each time a comparison. We don't have to run through all of the elements. It's always the same time for each search. And that's the big advantage of the index-based search. We just have to find an algorithm for the correct calculation of our elements. You now can test different limits again and so on. What you'll find is that you will have a constant behavior for the indexed, or almost constant behavior for the index-based search, and that you will have a linear behavior for the sequential search. So indexes which are later, so dates which are later, will cost more time in the sequential search, but it will cost the same runtime in the index-based search, and this is the big advantage. Therefore, let's go to question B of question number 3. There's just one question, why this code is still not so ideal, how it can be made faster, what could be changed to speed it up. The problem here is that you still have strings and that you have in some parts very complex structures. Therefore, you're very dependent on how efficiently and how good your programmed code is written. So, for example, if you always use loops for the search within the strings, it will influence the result tremendously. Therefore, it's really dependent on how good your code is. ASCII dates or ASCII numbers will always cost more time than pure numbers, and therefore, if you are able to convert your mechanism to a pure number without a very complex structure, so that you avoid conversions of types and so on, then it will be much faster. So that's question or answer for question number 3b. Question 4 deals with another sample which uses numbers. So in this case, the so-called Unix time or Posix time. In MATLAB, it's called Posix time. You remember it's called the epoch, and therefore it starts on the 1st of January 1970, 0 o'clock, 0 minutes. So the whole thing starts, and it always adds 1 second to the starting epoch. But therefore, you have to convert the dates before into this Posix situation with Posix time. So write a direct access using the Posix time and a conversion to index. And then measure the time for preparing your search date and compare it with the pure direct access. What is the real result and why? So what we do again is we create or we continue with our program here, and we create a first output and the start of the measurement. And then we exactly do the same what we did before. We did do the checks so that we know if the dates are outside of our range of the available data. So it's exactly the same what we did before. And then we do the calculation of the Posix time. So for the Posix time, we have to convert the search date string into intermediate type, which can be used by Posix time. So therefore, we convert our search date with date time to a date zone, and then we convert this to our Posix time. We do this for our search date so that we have finally a Posix time of the search date. And of course we have to do the same for the start date, because we use the start date again as a start point. In this case, we don't have to take care anymore on leap years, because if we subtract the search date or if we subtract the start date from the search date, then we automatically have the seconds between these two dates, which are already contain the leap days or leap seconds anyway, because we have the data available in our raw data set. And then we can calculate the index to our individual date in the following way. We subtract the start date from the search date, and then we have to divide it by 86,400, because we want to convert the seconds into days. So seconds into days, this is the number of seconds of one day. And then we have to do some fixing. So we have to adapt the index again. We have to add additional 1 for the headline. And the problem is now that the Posix start date, or if we do this subtraction, then we will end up with 0 if the search time is exactly the start time. So therefore, we have to add an additional 1 for the index, because MATLAB starts not with index 0, MATLAB starts with index 1. Therefore, we have to do 1 plus 1, or 1 or plus 2, which is for the headlines and also for the indexing, because the start date, if it would be the same date as the search date, would be 0. So therefore, we have to add this. I do a short comment to that so that I know why I did this plus 2. And with this, I will have the day index without any leap second comparison. And then I do the talk, and I just display the output. So this is the calculation of the Posix time and the index from the Posix time. So let's run the program again. We enter our date, and we'll see that our index-based search with Posix time is slower than the usual index-based, because we did a lot of additional calculations and type conversions. So to find out where the delays are, you can use TikTok before and after each of the elements. So let's do it here, and here, and here, and here. And then you will see, if we let it run again, that always the conversions will cost time. And therefore you should avoid these conversions. MATLAB is very dependent on if memory is already created so that it's easy to just load the data to an existing set of memory. But all of the conversions cost time, and therefore if you avoid these conversions, it will speed up your runtime. Also, the different functions have different runtime. So, for example, string to num or things like that might be much faster than the state conversions if there are different types behind. And therefore, you can maybe also use the Posix time from the column 3, so that you just take the first date Posix time corresponding element in the raw data, and then you convert it. And it might speed up your code. Or you do the preparations, as I said also during this video, always at the beginning, and then the rest of the search, all of the other things are much faster. So therefore, this is directly the answer for question 4b, where you will have the measurement of the different direct access methods, so that you see it's again a constant behavior, like with the index-based or direct index-based search, but it's slower than this direct index-based search, because we always have to do these conversions. So finally, what we want to do is we want to compare these different runtimes. So what we learn here is, again, what I repeated several times. So for the pure brute force search, so for the pure search where you always compare the elements, the sequential search, you will have a linear behavior. So it will increase as long you have to search. So for example, for indexes which contain data or date at the very end of your raw data, it will cost the most time. So it's this linear behavior. And for data which are at the beginning, it will be quite fast. All index-based accesses will have a constant behavior. So there will be almost the same search again. And then it's just dependent if you have an additional overhead, an additional constant, where it's shifted, so that some of the calculations are faster and some of the calculations are slower. So therefore, it's up to you how you program this and how good you are in programming. So that's it. This is the solution for the tutorial 7. I hope you had fun with the calculations. If you have additional time, try the binary search as well and compare it to the rest. And we'll see each other in the lesson. Bye-bye.